So this presentation is about isotonicity. It links with parenteral solutions in that we want solutions not to do any damage. When we give somebody a drug, we don't want to cause them more damage than we can help. So the first thing is just a quick reminder about osmosis, where there's a semi-permeable membrane, and in this case we're going to be thinking about the cell membrane of all the tissues in the body. Then water tends to flow in the direction that's needed to equalize out the osmotic pressure either side of the membrane. Hopefully most of you will remember this idea, the way that the water flows from area of low concentration to an area of high concentration. It's almost as if the solute that is concentrated is pulling in water from the far side. It needs a semi-permeable membrane, and obviously the cell wall or the cell membrane is a semi-permeable membrane. And that's why it's so important. So what we want to do is to make the solutions we want to give to people isotonic with body cells, so we don't want to cause any damage or pain. What can tend to happen is that, as you see here, with the hypertonic situation, what you get is you get cells sort of shrinking and becoming short of water and dying that way. With the hypertonic, then you get cells bursting, basically. Water is being pulled in, and that osmotic pressure can lead to damage of the cells. So really important that we get this right. And the tonicity is a property of the ions or molecules dissolved in it. So it's the particles dissolved in it that cause the tonicity. And there's a concept that, again, you kind of need to be pretty familiar with, is that when anything's dissolved in a solution, it lowers the freezing point. Incidentally, it increases the boiling point, but we're interested in the freezing point, and I'll go on to tell you why. Because see, how much a particular solute depresses the freezing point, lowers the freezing point, is used to work out how what its tonicity is, and that helps us know how much of what we need to add to make it isotonic. So we can look at a drug that we're giving to somebody and we can change the tonicity by adding something else. So usually solutions of a small amount of drug in water will have a lower osmotic pressure than body fluids. So we need to equal out those pressures by adding something else. And that's because, as you probably realize, body tissues contain quite a lot of substances within them as well as water. So therefore they tend to have quite high osmotic pressures. However, we can't do this by changing the amount of drug, because we have a particular dose that we need to give, so we can't just say, oh, we'll give a different amount of drug then. So we need to add something else to change the tonicity. Most of you will be familiar with sodium chloride as being common salt. It has a number of properties which are really useful to us in terms of medicines. So 0.9% sodium chloride, normal saline, is used in intravenous fluids because it's isotonic with body fluids. So 0.9% is isotonic. Normal saline will freeze at minus 0.52 degrees centigrade, as do bodily fluids. So we know that we've got a marker, we've got something that's very similar to the body tonicity that we need to aim at. So what we need to do is, whenever we have a drug solution, whenever we've added a drug to a solution, we will normally in calculations we'll be told how much it depresses the freezing point, and what we need to do is to try and adjust the tonicity by adding some sodium chloride to the solution to enable it to be what we call tonic or isotonic. And these values are found in textbooks. They've done lots of tests to actually come up with values for different drugs. So let's look at an example, fairly straightforward example. If we were making up an ephedrine hydrochloride solution, a 0.5% weight volume, as you can see 0.5 grams in 100 ml makes 0.5%. And we want to know how much sodium chloride we need to add to make it isotonic. How do we know it's not isotonic? Well, we look at standard values, and what it says is a 1% solution of ephedrine hydrochloride depresses freezing point by 0.169. So we know that that's less than the depression that we're looking for. And we also know that a 1% solution of sodium chloride depresses the freezing point by 0.576. So we are now thinking that we've got two values that we can use to be able to calculate what we need to add in terms of sodium chloride. So first we calculate the amount the ephedrine lowers the freezing point. So a 0.5% solution will depress the freezing point by 0.169, which is the standard value for a 1% solution, but it'll do half of that because it's half as strong. So therefore it comes out, it will depress it by 0.0845, and that's 0.0845 below freezing. Remember, we've gone now below freezing. So that's what contribution the ephedrine will make to the reduction in freezing point. But we remember we will need to go down to nearly to over 0.5. So we need 0.52 below freezing. So we've got to do something now to bring it further down. And what we need to do is to add sodium chloride. That's fine, but we need to know how much sodium chloride to add. So in this calculation, what we've done is we've said we've got the 0.52 is what we're trying to aim at. The 0.0845 is what we have already. So the figure that we've got that we need to aim at, that we've got to add to give the rest of the freezing point depression, is this one. It's 0.4355. Okay. We also know we've got to give sodium chloride to get that. So how do we achieve that? What do we know so far? Well, we know that a 1% solution of sodium chloride depresses the freezing point by 0.576. So to find out what strength of solution would depress the freezing point by 0.4355, you guessed it, we can use the proportional sets. So here we've got our 1% solution gives 0.576 reduction. Our unknown, which we've called Z here, we want to give 0.4355. And if we do all the clever stuff with the equation, what we get is 0.756% weight volume. That's the strength that we need to give in order to reduce the freezing point by the amount that we need to. You may need to go through this a couple of times. It does take a bit just to get your head around it. Once you have, it makes sense. Okay. So we're going to have to add 0.756% weight volume. So hopefully you can see that we need to know what volume we're going to actually add it to, because we've got to work out what the percentage is. This one was easy because we're making 100 ml, so we basically need to add 0.756 grams, because obviously number of grams per 100 mils is percent weight volume. So therefore we have 0.756 grams of sodium chloride. As I say, you may need to look at it again and go through and just understand the concept. You can look at freezing point depression. I put a link to quite a good YouTube video about it on Student Central as well. But you will quite frequently come up with questions like this in calculations exams, so it's good to be aware of them.